So welcome everyone. So today we have, it's my pleasure to introduce Utku Sirin from EPFL. He's a third year PhD student working with Anastasia Alamaki. He works as part of the Data Intensive Applications and Systems Lab at EPFL. And so he was here in the US for CIDR, so we managed to kind of divert him from San Francisco to Seattle for today. So he'll be spending some time here today after the talk, meeting with many of you. And in the afternoon, he's going over to the SQL Server building to meet with people there. So with that, welcome. Oh, one thing I want to mention that just recently announced that Utku won the MSR Fellowship Award from MSR Cambridge in Europe. So congratulations.
Thank you, Vivek, for the introduction. So hello, everyone. Thanks for being here. Today, I'll talk about our research on characterization of OLTP workloads that we did in the last couple of years. So we will concentrate on the interaction between OLTP software and the processor that runs the OLTP software. We will look at microarchitectural behavior of the OLTP software, and we will also look at power performance characteristics of different processors that are running the OLTP workload. So let's get started. So over the years, the speed gap between memory and processor are increasing and increasing. In this graph, on the left-hand side y-axis, you see the number of cycles that takes to execute one instruction. As you can see, it's dropping, it's going down over the years. And on the y-axis, on the right-hand side, you see the number of cycles to access DRAM. And as you can see, it's increasing over the years. And this gap tells us that as time goes, accessing DRAM costs even more, and we waste more and more cycles when we need to go memory and bring some data or instructions. So today's processors implement a lot of sophisticated techniques to mitigate these problems. They have heavily optimized out-of-order execution engines. They have deep cache hierarchies, a lot of execution units that can concurrently run a lot of instructions, and they have strong prediction capabilities. So what we are asking is, how are modern processors successful on executing database workloads based on all these optimization techniques? And this is a short answer for that. This graph is from my advisor's VLDB 99 paper. There on the x-axis, you see listed 3 databases, DBMS ABC, anonymized. They are all commercial disk-based databases. This is 99. And on the y-axis, you see the execution cycles breakdown into busy and stalled cycles. A busy cycle represents a cycle where at least one instruction is retired, whereas a stalled cycle represents a cycle where no instruction is retired at all. And what we see is more than 80% of the time, the processor here is Pentium 2, this is 99, and the workload is index scan based on a secondary index, so a lot of random data accesses. This mitigates the transactional workloads. And what we see is more than 80% of the time CPU stalls. This problem we define as underutilization problem, underutilization of processors by database workloads. So underutilization might actually mean several things. If you have 8 cores per second and if you have only 2 of them are active, that you can say you are underutilizing your cores because 6 of them are empty. This is not the case here. By underutilization, we mean that even the core is 100% active. In this time period, 80% of the time CPU is stalling, waiting to bring data or to do something to bring data or instruction to the processor and wasting its energy and performance capabilities. So this underutilization problem is our focus, and we're gonna look at this problem from different aspects in the talk. The talk is gonna be 2 parts. So underutilization problem can be understood from 2 aspects. You can look at it from software aspect, you can look at it from hardware aspect. From software aspect, you can think that the software, in this case it's the OLTP workload, is not able to utilize the processor features efficiently. For example, it doesn't have a cache conscious index, let's say, and it's not using those deep cache hierarchies as it could. From hardware aspect, on the other hand, it means the hardware does not actually give the opportunities that software can use. For example, software might have a lot of load instruction. It can be load and store heavy, whereas you have only 2 load instruction. You can do only 2 concurrent load instruction, and it stalls all the time because of the dependencies and so on. So in this talk, we're going to look at from both aspects. For the software aspect, we will compare disk-based and main memory OLTP systems. Main memory OLTP systems or in-memory OLTP systems are known to be implementing a lot of optimizations, including better cache behavior and so on. So there we will try to understand the answer of the question, can we mitigate this underutilization problem? Then we will look at hardware aspect, assuming for the scenario where we assume this underutilization problem is hard to solve, it's inherent. In this case, can we use low power cores instead of heavily optimized power-hungry Xeon cores to deliver similar performance by consuming low powers? And this will be the second part of the talk. So let's start with the first part. So in memory OLTP, they implement a lot of optimizations against disk-based systems. They omit buffer pool, which is a large component in traditional disk-based system, because they assume entire data fits into the memory. Then they use cache-conscious data structures. For disk-based system, it was disk access the bottleneck. Now it's memory access the bottleneck, and they want to mitigate this problem by using cache-conscious data structures. They use lightweight concurrency control mechanisms, meaning they might use no concurrency control mechanism and rely on partitioning. And for multi-partition transactions, they might use some special protocol. Or they use some optimistic multi-version concurrency control, which is known to be more lightweight than pessimistic versions. And then they use transaction compilation to further improve, further optimize the instruction footprint and eliminating a lot of function call overheads, function call or similar overheads within the instruction stream. So having all these optimizations raises the question whether the CPU utilization of disk-based systems and in-memory systems are similar, or whether we have any improvement on the CPU utilization of the transactional workloads. So to understand this, we took two disk-based systems, SureMT and DBMSD, a commercial closed-source disk-based system, and three in-memory systems, VoltDB, Hyper, and the commercial main memory system. We run two benchmarks over those 5 systems. We run a read-only micro benchmark where a transaction reads one row, randomly reads one row from a randomly generated 2-column table where columns are integers. And we run a standard TPCC benchmark. We keep entire data in memory to focus on CPU behavior. And we run all experiments as single-threaded to see the best case of the processors. We look at the execution cycles breakdown, just like I showed you a minute ago, where we categorize cycles into busy and stalled cycles. And then we focus on the stalled cycles and show stalled cycles breakdown to the cycles stalling due to the cache misses from the different levels of the cache. Yeah, go ahead.
So you mentioned doing single-threaded. Are these stalls anything that the hyper-threading can work around? So if you want two hyper-threads on the same core?
Yes, so it's kind of orthogonal, yes. With hyper-threading, typically it pollutes the cache. Now, you know, it's another thread and its instruction stream and data stream is potentially different. But in this case, we are turning off hyper-threading. It's kind of, you know, it's kind of an additional feature that needs to be looked at. We have done some analysis on power performance of hyper-threading. It typically improves performance like 40% for transaction workloads, yes, with additional power of a little bit more power, like overall energy efficiency increases like 20%. Yes, yeah. I mean, ideally, you know, yeah, it's substantial improvement. But in this case, we are trying to focus on like the best behavior of the core.
And it's not anywhere close to 100% improvement.
No, exactly. It's not TX at all. Yes.
So related to that, so how valuable would these results be? Because I mean, realistic systems are going to be multi-threaded. So, for example, stalls could be hidden in those kinds of cases, right?
So in multi-threaded case, typically you pin worker threads to cores, right? And so we have multi-thread results as well. I mean, so here I have in the backup slide for sure. We can talk about it. Typically, in multi-threaded case and single-threaded, the microarchitectural behavior are similar. So first, conflict is not that much usually if software is scalable, and the softwares that we are using are typically scalable. And in this case, if you think about per core worker thread behavior are more or less similar when you run all cores actively. We can look at multi-thread case as well, but typically conclusion is microarchitecture behavior doesn't change that much. Yes, I was saying execution cycle breakdown into busy and stalled. Then we're going to focus on stalled cycles breakdown into the cycles stalling due to cache misses from different levels of the cache. Let's start. So this is the processor that we are analyzing. It's an Intel Ivy Bridge processor. It has 2 sockets, 8 cores per socket. Its issue width is 4, so it can execute, it can retire maximum 4 instructions per cycle. Its memory is 256 gig. It's enough to keep entire data into memory. It has 32 kilobytes of L1 instruction, L1 data caches per core, 256 kilobyte L2 per core. Caches, and last level cache 20 megabytes. This is shared in the socket for all the 8 cores. So this is the, let's look at our results when running the micro benchmark. Again, the micro benchmark reads one row from a randomly generated 2-column table of size 100 gigabyte. This is single worker threaded and the processor is Ivy Bridge. So what on the x-axis of this graph, we list the 5 DBMSs, the 5 OLTP systems that we profile, 2 disk-based systems, 3 in-memory systems. And on the y-axis, we show the execution cycles breakdown into busy and stalled cycles. Again, busy is at least 1 instruction required, stalled is no instruction required at all. And this is 4 issue out of order machine, and therefore, stall means 0 instruction, whereas busy is only 1 instruction. So what we see is when running this workload, CPU stalls more than 70% of the time. And this tells you 2 things. First, for the disk-based systems, the advancements in the hardware over 99, whose graph I just shown you, is not helping to improve the stall cycle ratio of database workloads. And second thing is all these optimizations that in-memory systems implement is also not helping to improve the stall cycle ratio of transactional workloads. Now let's look at, go ahead.
Are you going to explain, like, for example, a system like OLTP, which is purely in-memory, optimized for in-memory and doing single-threaded execution per partition, and you only have one row, which means a transaction is accessing a single partition. What's the intuition behind why it's stalling so much?
Yeah, this is the whole talk.
Okay.
Exactly.
Okay.
So let's try to understand what are the reasons for that. And also, not just OLTP, Hyper and DBMS-M as well in memory systems. Like all these 3 systems, are kind of state-of-the-art in memory systems. Go ahead.
Yeah, I remember the Hyper folks reacting badly to this graph.
That's right.
And I thought that they had a point, which is if you squeeze your code down and your paths are very short, what's frequently the case is that it's harder to eliminate the data accesses than it is to eliminate some of the other instructions. So this could be what you could be seeing for the Hyper line at any rate is that they're very efficient at in between data accesses, and they haven't changed the number of data accesses all that much. And so this is a little bit misleading in terms of knowing what's bad versus what's good.
Sure. So here, this is like an overall result that we have. The next graph I'm going to show is going to be related more with like performance. Here we are seeing that even though you see like, I don't know, thousands X more performance, still processor stalls 80% of the time. This is more like what I'm trying to say from this graph. But reasons of this, like why this is the case, I'm gonna talk about it for sure. But I mean, so in the Sigmod presentation, I didn't show a performance-related graph. Now I'm gonna show. So that was more or less, one reason that they weren't very happy. But it's true. It's maybe unavoidable stalls. You're right.
So you're using this chart to blame the CPU, not the code, right? In other words.
Both, I would say. I mean, yeah.
Because if you want a high CPI or if you want a high line of code, if those are your metrics, then it's very easy to beef up your CPI or your
garbage. Yeah, for sure. You can trick the system, right? Like, spinning and so on. Yeah, you want performance as well, right? Performance is for sure there. Yeah.
So have people looked at using software prefetching to help?
Yes, not for this system. Like there's another system called Silo. They are using software prefetching.
And what is the ratio there?
Like software prefetching
Stalls to, what percentage
in
of
that
time it
system?
stalls? Yeah.
They have more or less similar behavior. Like overall stall cycle ratio is similar.
Despite using software prefetching?
Correct. This is like, things are kind of...
test patterns too random. You just can't, the hardware prefetcher only looks at
No, the software prefetching. They can modify the software to go prefetch.
Okay.
It's really hard.
So I mean, okay, so I'm looking at this system right now actually, and I'm in the initial phases of it. It is indeed true that software prefetching is very helpful on index traversal, but for example, in this case, for their versioning takes a lot of stalls. For some reason, they need to go DRAM and bring some like fresh copy of the version for each node. Like concurrency control, brings a lot of stalls for in this case. But overall behavior is similar.
So have you looked at the number of concurrent outstanding misses that this processor can have?
Yes, this is, you mean like, from L1?
From the L3 to memory.
L3 to memory.
10 per,
I look.
10 per core.
10 per core. For L1 it is 10, for L2 it's 16 that I know. For L3, if I'm not mistaken, I couldn't find it in the software optimization
There
manual.
are 10 fill buffers.
Okay, 10 line fill buffers. Oh, I see.
That's what limits it.
Okay. Thanks.
Well, that's informative. Anything else? So I'm going. So yes, we have very high performance, but stall cycle ratio is still bad. And let's see why is this the case. So now let's first look at what are those stalls for each system. So in this system, in this graph, x-axis is again showing the systems. On the y-axis, we show the stall cycles for single transaction for every system. So we run the transactions, and per transaction, how much stall each system incurs is shown by this graph. And for each stalled cycles, we break down it into 6 categories for 3 levels of caches, separately for instruction and data. Each bar in this graph has 6 components: stalls coming from L1 instruction, L2 instruction, and L3 instruction, L1 data, L2 data, and L3 data. And what we see here, main memory systems per transaction indeed incurs much less stalls. This tells us those optimizations are actually helpful to reduce the number of stalls per transaction for every system. Then the question is, if we incur less number of stalls, how come the total stall cycle ratio is high for main memory systems? And to understand the answer of this question, let's do the following. For every transaction, let's take this number, the number of stalls per transaction, and let's divide it to the number of instructions per transaction, and try to understand how much stall we have to execute one instruction. Because in terms of processor doesn't know anything about transaction. Transactions is software level abstraction, as a metric. In terms of processor, it's the number of instructions that's executed. And now let's look at this. How many stalls we would incur per instruction? Then the graph would turn out something like this. Here on the x-axis, again, we show the systems. On the y-axis, we show the stall cycles that's break down into six components. And they are counted per instruction. What we observe is that when you look at per instruction, you again see that for all the systems, the number of stalls are more or less similar. They are very close to each other. So it tells us that the complexity of the transactional system, even though they are very optimized, is beyond the capabilities of the general purpose processors, so that to execute one instruction, you still need to stall a lot. And now let's look at what are those stalls for the 3 main memory systems to understand the behavior better. If you look at VoltDB and DBMS-M, you see that L1 instruction stalls are still main components, just like the disk-based systems. This tells us to execute one instruction, most of the time you don't find this instruction in the L1 cache, and you wait to bring this instruction from cache from memory or L2 cache to the L1 cache. This tells VoltDB and DBMS-M instruction footprint are still significantly complex, that they majorly suffer from L1 instruction stalls. Whereas for Hyper, you see that L1 instruction stalls are almost disappeared. Hyper implements an aggressive transaction compilation technique that compiles the transaction directly into the machine code. This eliminates a lot of instructions, such that entire instruction footprint of Hyper fits into the I cache, L1 instruction cache. When we do this, however, we observe that last level cache data stalls are amplified. So this reveals the following fact. Okay, for disk-based systems, we knew that instruction footprint was large, and it was very complex for the processor to execute it. And it was suffering from L1 instruction cases. If you don't do aggressive transaction compilation, this is the same case for VoltDB. This is the same case for in-memory systems as well, as you can see for VoltDB and DBMS-M. If you do aggressive transaction compilation, eliminate the complexities in the instruction footprint, the fact that the data footprint of transaction processing systems are also very complex and beyond the capabilities of the general purpose processors, such that they stall majorly from data stalls, and such that the transaction processing system starts suffering from data stalls rather than instruction stalls. Hence, we are concluding that main memory systems, if main memory systems are still have a large stall cycle ratio, if not from L1 instruction stalls, this time from data stalls. And this is, go ahead, please.
Well, I'm just curious how you measured the stall cycles from L1I and L2I.
Sure. So here we're simply counting the number of misses, and we're
You're using the L1I miss event.
Correct.
Did you cross-check it with using? There's an event that measures if the the resource, the scheduler is empty.
Resource
Much-
scheduler,
Yeah.
like in the pipeline.
Some RS empty, blah blah, something RS empty. It's tends to be a good, better way to do it because it actually, the event exists on every.
I see. I didn't know that. Sure, no, we haven't checked it. Okay, look at it. Thank you.
Because this does speculative stuff. And
I see.
It's very hard to get this. this-
No, for sure. There are a lot of overlapping as well. This is like a simple way of counting those things.
Yeah, no, exactly. That's why I recommend the other one.
Sure, yeah, sure. I'll look at it. Yeah, for sure.
Maybe it's not very relevant, but I mean, is Hyper faster than VoltDB or not? I mean, this is all relative, and I'm trying to get my head around that. I mean, you're not showing any absolute performance, which is what really matters. But
Sure,
could you
but-
just comment a little bit on that?
Yeah, of
or
course.
are they all the same in performance?
No, they are not the
Prior
same.
slide, show it?
Say again?
Yeah, that's fine.
Yeah, exactly. This more or less shows you the performance, right? So this is number of stalls
Oh,
per
okay.
transaction.
Okay.
You know, these
So
guys,
okay, so that okay. Got it.
if you actually divide this one to that, you get absolute performance numbers, you know, number of transactions per second. So Hyper is, you know, significantly larger than the other systems. But you should think that this Hyper is demo version of Hyper. It has its own indexing and so on, but yeah.
Okay. So I don't see what so it is a good idea to what Hyper is doing, right?
For sure,
It's
for
just,
performance, yeah.
Yeah, so you're just fighting the next bottleneck.
Yes, correct.
Okay,
Correct.
got it.
Yes, exactly. It was instruction stores was the bottleneck. Now it's data stores was the bottleneck. And data stores are sort of harder to mitigate because, as they just pointed a couple of minutes ago, they might all be unavoidable stores here. It might be that they are all raw data. This is like the most important question here is what are those data stores, right? Can we reduce this to here, right? This is an important question. Yeah, and I don't have much hope, but we are looking into it right now. If at the software level we can reduce these stores so that you can have high performance without much stores.
So Hyper is pre-compiling the transactions to machine code.
Correct.
Now, at what point? So let's say you have 100 transactions, 100 distinct transactions I need to support
Okay.
for my app.
Okay.
Then how does that instruction cache misses change? As the-
100 different transactions you
So
have.
how big are these instruction caches? Can they scale with number of transactions?
So okay, so one transaction in Hyper is around 1,000 instructions. So 1,000 instruction, each instruction 4 byte, let's say, it's 4,000, 4 kilobyte, yeah. And L1 is 32 kilobytes. I mean, when I talked to Thomas Neumann, builder of Hyper, he was saying 32 kilobytes is more than you needed. I don't know based on what he's saying is, but you know, 32 kilobytes is large enough. Was his comment? You know, yeah. I think it depends on your system because you know, for example, okay, VoltDB is also very optimized. You know, it doesn't have buffer pool, it doesn't have locking and so on. But still, but VoltDB has Java front end. You know, this is like a significant component for VoltDB. From there, a lot of instructions are coming, and this causes like performance drop.
Yeah, but following up on Vivek's question, if you had a lot of different transaction types, which produced a lot of different compilations, and especially if they were on shared data, you might see something very different because you'd be sort of forcing the L1 cache to an I cache to be not so well used.
Yeah, that's true. I'm going to show TPCC results in a moment where you have 5 transactions, for example. There you will see a little bit of L1 instruction. And if you have 100 transactions, maybe you're right. That's actually a very good point. Then maybe you're going to be even worse than this, right? It's like a trade-off. That's true, actually. It's a very nice comment. But okay, like overall, L1 instruction stalls is. Go ahead.
I have a question. So, if you had like a million transactions on one core and you plotted this, and if you ran the same workload on 2 cores with 500,000 transactions each in parallel, how would the data stalls change? I mean, do you have like a graph that shows, because I mean, since now you're leveraging 2 separate access paths to the memory subsystem, right? So you presumably get better overlap of these data retrieve instructions.
So overlap, you mean, but at the end of the day, you use both core 100%, no? Like both cores are active at 100% level. Either it's 500.
Yeah, but the memory subsystem you probably can eke out more out of the memory subsystem if you're accessing it from 2 different.
So you mean like one core is gonna find some shared data structure already in the cache and so on?
One is that, or I believe that the memory subsystem gives aggregate better throughput if you're accessing it from multiple code. So,
If you can use multiple channels at the same time,
Yeah.
you've got more bandwidth out of them.
right.
I see. So we did look at multi-threaded case. Let me just check a backup slide for that. Go. Yeah, multi-threaded. So this is per 1,000 instruction rather than per single. So this is multi-threaded case. There's no hyper. And you see more or less similar trends for disk-based. So this is all cores are active. You have 8 cores or 16 cores, 2 sockets, all of them are active. And this is per thread, like in one thread, you look at it. And again, you see, for example, these instructions are bottleneck. This is TPCC, by the way. Instruction stalls you have for this, and some data stalls here. Whereas for disk-based systems, you have mostly instruction stalls. More or less similar trends follow. I mean, from my perspective, it's like sort of, partitionable, like, because, I mean, okay, in TPCC, you have, multi-partition transaction, like 15% or something. You have some conflict, but not so high, it's not like very contentious. For high concurrency, like high contention, we haven't looked at it actually. That's actually an interesting point. Maybe this is like another point in the design space. If you have high concurrency, maybe things are different. But for TPCC, most of the time you get similar results with multi-threaded.
Are all these measures based on independent events, or is it constrained to equal your stall cycle count? Are you doing any of these measurements by doing a subtraction?
Subtraction. No,
Stall cycles minus L1I minus L2I minus L blah 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 equals LLCD.
I see. No, they are independent events. Like
Okay.
iCache misses,
Just
L2 misses.
checking.
Yeah, cool. Sure, absolutely. I mean, VTune gives you these counters that exposes those counters, so you can. I know, but it's hard to work with counters. Yeah? You don't. Yeah. Maybe It's there are a lot of stalls that we don't count, for example. Which what are you gonna do?
Right, these are explicitly counted. I just wanted to check.
Yeah, sure. They are independent events for sure. Yeah. Okay. So this was for micro benchmark where a single transaction, same transaction reads one row. Now, okay. So now let's look at how come those instruction stalls are still problem for VoltDB and DBMS-M. To do that, we take our micro benchmark where we read one row per transaction, and we increase this number from 1 to 10 and to 100, so that we increase the size of the transaction more and more, and also the instruction locality inside the transaction. And let's look at what happens then to the instruction stalls and see if there's any interesting pattern to understand the behavior of those VoltDB and DBMS-M with large instruction stalls. So for here on the x-axis you have DBMSD, disk-based system, VoltDB, DBMS-M, and on the y-axis you have stall cycles per instruction again, which is what matters for processor. What we see is, even though you have like a for loop in the instruction in the transaction that successively probes random rows, for DBMSD instruction stalls are still the major bottleneck. There is some reduction on L2 instruction, on L1 instruction stalls are still there. This shows the really high instruction footprint of the disk-based systems. When we look at VoltDB, you see that L1 instruction stalls are similar to disk-based when it's one row per transaction. But when you increase to 10, you immediately see a significant draw on instruction stalls, telling us that the OLTP engine itself, when you concentrate on the transaction, does not have that large instruction footprint, which actually in one sense we have shown by the number of stalls that per transaction in the first graph that I've shown you. And when you go 100, the instruction stalls are really small. For DBMS-M, on the other hand, when you increase the number of rows read per transaction to 10, still L1 instructions are large. It goes to slow value only when you increase the number of rows per transaction to 100. This shows that DBMS-M's instruction footprint are still significant. I mean, the inside OLTP engine, it has low instruction footprint, but but the outside of the OLTP code engine, where you have query parsing modules and so on, they are effective. They are important to contribute to instruction stalls and suffer system mostly from instruction stalls. Let's look at this problem from another perspective. With the same analysis, now we have done best effort categorization of the modules that each system executes, and we categorize the number of time, the percentages of time that spent inside OLTP engines. Here again, we use the same micro benchmark. We increase the number of rows per transaction from 1 to 10 and then to 100. and look at how much time each system, DBMSD, OLTP, and DBMSM, spend inside the OLTP engine. We see similar pattern here. If you look at the DBMSD, does not spend the increase in the number of time inside the OLTP engine does not increase for DBMSD. For VoltDB, however, it increases significantly when you move from 1 to 10, as in the L1 instruction stalls are decreasing here. And for DBMSM, the main memory engine, commercial main memory engine, you see that the time you spend inside the OLTP engine does not increase for 10 rows per transaction and increase significantly for 100 rows per transaction, which corroborates the following trend, where you have significant drop in L1 instruction stalls only when you move from 10 to 100 instructions per second. So here, the conclusion is that the instruction footprint of the OLTP engine is small. Those optimizations are helpful. But the outside, because DBMSM is an OLTP engine for a disk-based traditional system, it uses several modules from that. It borrows similar modules from disk-based systems, and that contributes to the instruction footprint. But when you increase the size of the instructions significantly, then you spend a lot of time inside those optimized main memory OLTP engine, and therefore your instruction footprints, instruction stalls are reduced. So these were the results for microbenchmark. Let's now look at the real-life workload TPCC to see if there is anything different. So this is the stall cycle ratio. On the x-axis we have the systems, and on the y-axis we have execution cycles breakdown to busy and stalls. We observe that still 60% of the time CPU stalls, majority of the time CPU stalls, similar behavior with the micro benchmark, though it's a bit better behavior than the micro benchmark, because TPCC transactions have some sort of locality inside the workload. Micro benchmark was all random data accesses. And therefore it is a bit better in terms of using the processor. Nevertheless, it more than half of the time CPU stalls. Again, number of stalls per transaction for different systems. Here we observe that again, main memory systems has significantly lower number of stalls per transaction. Hyper has lowest among the others, showing that it's highest performant. And when we zoom into the inside the transaction and look at stall cycles breakdown per instruction, we observe similar trends with the micro benchmark. For disk-based, L1 instruction stalls are main bottleneck. For VoltDB and DBMSM, not using aggressive transaction compilation, still suffers a lot from instruction stalls. For Hyper, on the other hand, data stalls are the main bottlenecks because of its aggressive transaction compilation. The bottlenecks shifts from instruction to data stalls. Although here you start to see a little bit of L1 instruction stalls when it comes to TPCC, which I think relates to the point David made a couple minutes ago, where you have more transactions that you need to keep in the L1 instructions. Then you actually have, you start to see some instruction stalls. Maybe if you have 100 transaction types, maybe then it's even worse than the other systems. That we haven't looked, but it might be the trade-off that transaction compilation needs. But for our purposes, it shows that it is effective to reduce instruction stalls.
How consistent is the reconstructed stall count with just a direct measurement of cycles with no retirement?
Cycles with no retirement. So like how consistent it, like relating with this to this this graph?
This to that, yeah.
Yes. So okay, here. This is like a linear decomposition of the cycles.
Right, this is just UOPS retired.
Exactly. Yeah, exactly. That's true. Yeah. Among these stalled cycles, it's most of the time more than 50% are memory stalls, like 50-60%, like this linear decomposition. Majority of memory stalls. Memory stalls meaning cache accesses. And so what can you have? You can have branch misprediction.
No. I'm just wondering. You're counting. You've got a total count of the run of stall cycles from this.
Yes.
And I'm just wondering how consistent that number is.
Like if you
with
sum
the
up.
sum of the other.
Oh, okay, yeah. So this is much larger than this sum of these. Absolutely, because of course it's significantly larger. But because we are not able to count a lot of stalls. I mean, I talked to an Intel guy, like saying that you see there are like a lot of stalls. I mean, like half is there, but the other half, where are those half? He said we can't measure them. There are not enough events to measure those stalls. I don't know. I mean, I look deeply. There are like 422 counters. I look like each and every of them. Oh, 2000. I don't know, maybe. So, and I don't know. I couldn't come up with like a, because ideally what you could do is like complete breakdown. Like you sum and you get like more or less the same number of cycles. You know, that I couldn't achieve. This is like a classical way of we do in the lab of like, you know, evaluating misses, evaluating stall cycles. Focus on that. Sounds good. Sounds good. Okay, so for TPCC we see similar trends with the micro benchmark. Is our conclusion. Okay, so to sum up, in-memory OLTP underutilizes the processor. If not aggressive transaction compilation, it suffers a lot from instruction stalls. If uses aggressive transaction compilation, it reduces L1 instruction stalls, but that manifests the last level cache data stalls, resulting in high stall cycle ratio. So, okay, underutilization problem, now we have looked at the software aspect. The question was, can we mitigate underutilization? Okay, the answer is, I don't think it's very easy, because in-memory OLTP systems are already doing a lot of improvement, a lot of optimizations to actually improve the busy cycle ratio, but it ends up with having high stall cycle ratio. That it doesn't say, but it suggests that it looks like an inherent problem for transaction processing system, that having high stall cycle ratio. Here, of course, the way to understand it, to look at what are those stalls, right? Are they coming from, are they raw data stalls? Are they coming from B3 indexing? Are they coming from, you know, synchronization primitives like locking, or if you're using, I don't know, anything else that you're using? But the overall comment that I would have is, if it's coming from metadata access like locking or B3, this is improvable. We can improve this because we know what we are doing over there. We can use some cache-conscious data structures, logging schemes, and so on. But if they are raw data, which they seem to be, then it seems that we have reached the hard limit. And it seems that whatever you do, this processor is gonna stall. And at this point, the only thing that you can do is look at the hardware and how can we either adapt the hardware, or maybe instead of using this hardware, use some low power cores, so that you can save maybe some power, which is the next part, which is gonna be the next part of the talk. Assuming the scenario where underutilization problem is inherent, now let's look at can we run transaction processing systems on an ARM64 core who is consuming much less power than Xeon by delivering satisfactorily high performance and also consuming low power. To do that, we compare a power-hungry Xeon core with an ARM64 core. Let's move to the second part of the talk. So ARM has recently announced its server-grade processor. It is somewhere in between Atom-like lean processor and Xeon-like fat processors. Its microarchitectural structures, main microarchitectural structures, are very similar to Xeon. It has 4-way fetch, decode, rename, dispatch unit. You can issue 4 instructions at a time, just like IV Bridge. It has a number of execution units that can concurrently run different instructions. It has deep cache hierarchies, 3 levels of caches, and so on. So majorly, it looks a lot like to Xeon processor. Here, we will look at when running transaction processing workload, whether those ARM server-grade processors are delivering satisfactory high performance and also maintain low power consumption characteristics. Because when you embed that much microarchitectural structures inside the processor, you're also likely to have higher power consumption. So now we're gonna look at power performance characteristics of ARM versus Xeon when running transaction processing workloads. To do that, we took one disk-based system, SureMT, and one in-memory system, Silo this time we took. So the other 3 main memory systems that we profiled, VoltDB, Hyper, DBMS, AMP, they are not portable to ARM. VoltDB is Java. I haven't tried Java on ARM, maybe it is, but to my knowledge, it's not as easy. Hyper is closed source, DBMS, AMP is closed source, whereas Silo is C++, so we were able to port Silo into ARM. Therefore, we pick Silo. It's also a very high performance system, so it's representative for high performance main memory systems. We use TPCC benchmark, 5 GB of data, and we keep the data always in the memory. 5 GB might seem a little bit low to you, but our ARM server had 16 GB of memory. 16 GB of memory, and 5 GB was the kind of the optimal point that we could do our experiments. Nevertheless, this is orders of magnitude larger than the cache size. So more or less your cache behavior, your stall cycles ratio would be similar. So it's enough to be representative to compare the cores. And then we compare Intel Xeon processor with an ARM Cortex A57 code, a commercial implementation of ARM Cortex-A57. This is ARM's first server-grade processor announced. It's announced on 2013, I guess. Now they advanced it to A72, which is kind of more high performance. But this is explicitly designed for high performance server workloads. We're going to compare these two cores in terms of the throughput they deliver, in terms of the power they consume, and in terms of the latency that it takes for the transaction processing system to finish a single transaction. We focus on active power consumption, meaning we populate the data, we measure the power, wall socket power, real power. Then we run the system on the populated data. We again measure the wall power socket. We take the difference and use it as an active power consumption value for the processors. This is our methodology. So these are the comparison of the two cores. As I said, the main microarchitecture structures are similar. So Intel has 2 sockets, ARM has 1 socket. We close 1 socket of Intel, so it does not consume power. They both have 8 cores per circuit. They are both 4 issue width. Their issue widths are both 4. Their clock speeds are the same. Their cache hierarchies at the first 2 levels are exactly the same. Last level cache, Intel has 20 megabyte, ARM has 8 megabyte cache. They are shared for the 8 cores for both of them. So this difference might seem significant, but for transaction processing systems, it's usually known that more than 4 or 5 gigabytes of last level cache does not matter for performance because you have a lot of random data accesses and data does not fit in cache anyway. It's important to keep the cache. It's important to have cache as large enough to keep the instruction footprint in the cache, which is couples of megabytes maximum. So main microarchitecture structures are similar. What is different? It's the inside of the core. Pipeline side different. How optimize it? What we're gonna investigate in the analysis. Let's look at our first evaluations. Here on this graph, we present a single core evaluation. We have 3 graphs. The left-hand side, on the left-hand side, we use the throughput values. On the right-hand side, we compare power values, and on the right-hand side, we get the net results of power throughput, which are energy efficiency. The workload is TPCC, it's 5 gigabyte, a single worker thread, and the system is disk-based short-empty. So what we see is, while Xeon provides only 1.7x higher performance, it consumes 14x more power than ARM, rendering ARM 9x more power efficient than Xeon. So this tells us when running a disk-based system, ARM is indeed a promising alternative to Xeon because of because it delivers satisfactory high performance while also maintaining its low power consumption characteristics. So this is a disk-based system. It has a lot of disk-based system. It has a lot of overheads. Maybe it's not representative for today's high-performance systems. Now let's look at the analysis when we run Silo. So here we again have single core evaluation for the same workload when running Silo. What we see is Xeon this time delivers 2.5x higher performance than ARM, but it still consumes significantly larger amount of power than ARM, making ARM still significantly more energy efficient than Xeon when running the transactional workload. In terms of throughput, we have 2.5x difference. In terms of power, we have 15x difference, and net results of these two, we have 6x higher energy efficiency for ARM than Xeon. So this again tells us ARM is a promising alternative in terms of energy efficient computing.
Something like 10 watts.
Say again?
The ARM processor is running something like 10 watts.
Single core, so entire server is like 45. Per core, it's like 3 watts.
No. I mean measuring just the socket directly.
Entire socket.
Just the socket.
So okay, so
Ignore the rest of the system, just because the complaint you're going to get with the Xeon's got all this stuff in it.
Yeah,
right?
sure. So
it may be useful to just measure directly the socket power directly and just
can we do that? Because what we are doing is we're just measuring the wall socket power, like the entire server. We put the power meter to the sockets, wall socket.
You can certainly do it on the Xeons. I don't know about on the ARM.
On the Xeon, okay, like you can do the real-time power measurement. Yeah, we can. There are counters for that.
There's an MSR.
Exactly. Yeah, that's for sure.
Alternatively, if you've got a sensor on the voltage regulators, you can read it through the BMC with ITMI.
I see. That's okay. That I didn't know. So this maybe we can do for ARM as well, right?
Yeah,
because it's physical.
That would work for both if you have a voltage regulator that has a sensor.
I see. Sure. For this, we didn't do that. It's like, yeah.
So I'm trying to, so this was the processor's power consumption or the blade power consumption?
Processor.
Because this may be an example where what you're showing is that the Xeon, if you consider the entire power course, the Xeon might be in fact more effective because it's got higher performance, and yet you're only changing the total power consumption by a very small amount by looking only at the processor part.
You mean like, you're saying for single core versus multi-core, or like entire system?
Suppose the memory was 100x the power consumption of the processor. Now, I really don't know what it is.
Yeah.
Suppose it was 100x.
Yeah.
Then what you'd be doing is you'd be showing the difference in the 1% of the power that goes to the processor, right? Yeah. And so the 2.5x that the Xeon gives you is in fact almost 2.5x in terms of power effectiveness as well, because you really the power doesn't change that much between the two.
I see. So for the server that we are using, I haven't done the entire breakdown of the server, how much it goes to memory, how much. But there is a study on SIGMO 2010 showing like a classical database server using similar processors that we use, using similar memory size, and there it's mostly active power consumption of the processor dominating the total power breakdown. It's around 50% of the entire server is processor's active power consumption that we're measuring it. Sure, rest like half, the other half, memory, disk, static power consumption, and so on. But like current knowledge is that most of the time in a DB server, in a classical database server, most of the time its processor is consuming the majority of the power budget. So this is like the information that we are basing our.
So just looking at these. What you have up here, if the processor represented about half of the power,
yeah,
then you would in fact be having the normalized energy efficiency difference. I mean, because you're only,
I see, like,
only optimizing 1/2 of the.
That's true. No, that's true. Yeah. So yeah, I don't have the graph right now, but that's true. When you put the other sides of like the entire server thing. Yeah, for sure. So performance is very important, right? I mean, like everything in the server you put to make higher performance. When you have 2x higher performance, you have 2x higher energy efficiency. When you lower the CPU power half, you don't have 2x. You have like less higher energy efficiency. That's for sure true. But yeah, it's like this. It's hard to have higher performance sort of, and then it's like another design, another space in the design. For example, when you consume lower amount of power, you can put more cores maybe to the same power budget, and then you can maybe have more, you can have more performance because you can put more cores in the same power budget. This can be an alternative to using power-hungry Xeon servers. But yeah, if you look overall energy efficiency. Yeah, I think data would tell us. I can't tell in this case ARM would be more energy efficient or Xeon would be energy efficient. But that's certainly an important point. You're right.
Another issue too is that because you're using a single core here.
Yeah.
When you use all the cores, it might be that Xeon is going to be more than 2.5x higher throughput.
Next slide. Yeah, exactly. Yeah, that's true. Multi-core is for sure is another point which I'm going to show in the next slide. So okay, this is single core evaluation. Let's look at when we increase number of cores, what happens. So here we have 3 graphs for throughput, power, and energy efficiency. System is sure empty, TPCC 5 GB, and on the x-axis we increase the number of threads. Each thread is pinned to one single core. Now let's look at trends on Xeon versus ARM. So in terms of throughput, we see that throughput scales linearly for all systems. This shows that software system does not have inherent scalability bottlenecks. The difference is around 2x even for all number of cores, number of threads. For normalized power, on the other hand, you see that the incremental amount of power that each processor takes to turn on new core are more or less the same. If you look at this incremental power, they are more or less the same for both. But Xeon has this base power consumption that it carries all the way to all the way to 7 cores. And this base power consumption makes Xeon very energy inefficient. But since it has higher performance, its energy efficiency, it keeps increasing and increasing when you look at the net results of power performance. So if you look at the energy efficiency graph of both processors, you see the following fact. For ARM, the performance and power curves are going hands in hands. For example, if you're running one thread and you're delivering X amount of throughput, you consume X amount of power. Then for 4 threads, you deliver 4X throughput, then you consume 4X power. So more or less, the energy efficiency is constant. When you divide the throughput with power, energy efficiency difference is not that much. This is called energy proportionality. So when you turn on more number of cores, you proportionally increase your power consumption. Whereas for Xeon, you see that energy efficiency is always increasing because the additional throughput is always significantly larger than the additional power that you consume when you activate more core. So this is good to have large energy efficiency, but this is also bad if you don't have all cores active, right? Because if your utilization, if the number of active cores is around 3 or 2 most of the time, then it means you're much less energy efficient than you could be when you have all cores active. So this tells us ARM achieves this feature called energy proportionality. It's consuming power proportional to the throughput it delivers, whereas Xeon suffers this large base power consumption that makes it energy inefficient. So for the point that we were saying, like when you have more cores running, it's true that performance, for sure, energy efficiency increasing, and this gap is closing and closing, right? But still, this is lower than this, and around this region, for example, it's reported that for Google, it's 30%. Most of the time, only like 3 of 10 cores are active. For Twitter, it's 20%, average load, typically. So in this case, Xeon, wasting a lot of time by having different cores, by having different cores consuming power. Whereas ARM can be good in this sense. But that's also true that this is only for, ARM achieves energy proportionality at the core level. If you add power of the memory, disk, and so on, it's not energy proportional. Still, it has large amount of power. But you need to start some point, and ARM seems to be, is a promising choice if you would like to end up with an energy proportional server. So this is for sure empty. Now let's look at for Silo. Again, we see performance are scaling linearly for both cores, and the ratio of performance are similar. This is 3x more or less all the time. Power, again, the incremental amount of power to turn on one core is similar for Xeon and ARM, whereas Xeon has this large base power consumption. And when you look at the net results of these two graphs, energy efficiency of ARM is more or less constant. This difference between that point and 7 is more or less 20%, whereas Xeon's energy efficiency are increasing and increasing. In fact, when you activate all cores, it's very close to ARM's energy efficiency value. This difference is 15%. If you assume this is 100, this is 85, which is good, having an increasing energy efficiency. But on the other hand, it's bad if your utilization period is around 20% and 30%, means you waste a lot of power. And one thing I forgot to tell, so why is it the case that Silo is better for Xeon, right? Why is the case? Silo is, as I've shown you, reduces instruction footprints, main memory system, so it stresses on more the out-of-order execution engine. And this is more developed in Xeon. So it delivers higher performance when running Silo than when running short empty.
Did you turn on core C states?
That's exactly what I was going to ask.
You mean here, C states are available.
Did you enable? You got to go into the BIOS to enable.
They are, yes.
Enable P3 and
yes, they are enabled.
C6 core
yes.
states.
Yes, that's true. They are I didn't enable it. It was enabled by default. Yeah, definitely. Yeah, C states. Yeah, that's true. Right.
Core C states.
Yeah. No, they are enabled. 0203. Yes. They were enabled by default. I remember I checked them.
Okay.
Yes. Okay. So energy proportionality. So now let's look at another metric to evaluate the cores, which is latency evaluation. So recently it has been shown that for high fan-out, highly scalable systems, even if you have 1 out of 1,000 servers are responding high latency, then it can bottleneck entire system that the overall outcome is high latency. So you would like to have all your servers, like 99% or 99.9% of your servers responding low latency rather than just average latency being high. So to do that, we look at tail latency evaluation. Tail latency represents the latency values that sits the tail of the latency distribution, like at the 99% and 99.9% are the percentiles that we are interested in at this point. So we do latency analysis when running Shore, empty, and Silo, and compare ARM and Xeon again. Here, at this point, we have all cores active, and the workload is same. TPC is 5 gig. What we see is if you're running Shore empty, your average latency around 2x, as in corresponding to throughput basically. But your tail latency values are also in the boundaries of 2x. It's for 99 and 99.9%. Whereas for running Silo, your average latency is around 3x different, so it's 3x higher when running ARM. But your tail latency values for 99 and 99.9 percentiles, it's significantly larger for ARM than Xeon. So this represents a scenario where Xeon is a clear winner against ARM.
Yeah, I'm not a database person, but that would look like a deal breaker, right?
Yeah, like you mean,
That
yeah.
you just can't possibly use ARM.
It depends on the workload. If it's tail latency critical, it's very hard. Yes, I mean if it's like you have strict
A
requirements.
lot of this may be OS recovery and thread blocking and scheduling and so on, and all of this being ported onto ARM is kind of new. So
Do you have a breakdown
give
of,
him a chance.
do you have some sort of breakdown of where the extra latency is coming from? Or no?
Where
So do you have some sort of breakdown that says the extra latency is coming from scheduling or it's coming from?
No, but this is the same software stack running in both cores. It's probably in the
The
software.
interrupt handling is hardware specific.
What's hardware
The
specific?
interrupt handling ends up being hardware specific.
I
the way
see,
that
like at the
works.
hardware level.
And it
Yeah, I
may not be well. Give him a chance. That's all I'm saying. I'm not sure they're going to win either, but give him a chance.
That I don't know. I mean, yeah, maybe like this
hard to
interrupt
do.
stuff, and yeah, it's different. But like what we are looking at per transaction, at the end of the transaction, we measure the latency and save it for every finished transaction.
So for database systems, isn't tail latency so the most critical performance?
So for database systems, particularly, transaction processing are known to be latency critical. That's true. For tail latency, I haven't seen any study that stressing it's important for the transaction processing systems are like tail latency critical. I have seen for tail latency mostly for like scale out workloads like Facebook and so on. More like you need some fluent like high fan out, highly scalable system. Like in Facebook, for example, you scroll and you need like fluent flow of your newsfeed, these kind of things. For transaction processing, I have like latency critical. It's known to be latency critical compared to analytics, for example. But tail latency critical, I am not sure. I mean, we can assume this for sure. And this is, we can assume that this is like a clear winner for Xeon for sure. But it depends on vendor. It depends on like real values. Maybe this 11x is acceptable for them, like SLA. Like somehow their customer is happy. But this is for sure true that like this is a very important reason to pick a lot of companies Xeon rather than ARM. This is very important for a lot of companies. That was, for example, that was the reason that I did this analysis, so that if ARM is like adequate from all aspects, which tells us it's not for latency.
But since the 15th percentile latency is also 3 times higher, does that mean the average latency is also more than 3 times higher?
Sure, yeah, 50 and average latency are closer, yeah.
So,
it all depends on your customer, right?
So, but just extrapolating from this, right? This shows that for transaction processing systems, ARM might not be a great solution. If you think of HPC systems, you would expect ARM not to do so well, again, because when you look at pipelines and you have a lot of instructional level parallelism and so on, you would think that Xeon would beat ARM in that context as well. So, right, so are we sort of constraining the ARM scope to cell phones and things like that, or?
Maybe storage servers.
I don't understand this concern about latency. I mean, really, it depends upon what the absolute numbers are. If the latency of the database or the latency of the transaction is, if you're talking about microseconds of latency, then it probably doesn't matter whether it's 11 times as much as somebody else.
That's true.
If you're talking about tens of seconds, then 11x would be a killer, right? But a lot of these transactional systems, the transactions, especially in the main memory case, are really, really short. And so whether or not you're running a 1 microsecond a transaction or 10 microseconds hardly matters, right?
But
throughput is
it's
much
highly
more
unlikely that they're running at microsecond speed, right?
No, it's mostly
It's not impossible.
It's possible. I mean, in our case, it's around it's in orders of microseconds. For silo, for sure empty, it's milliseconds, but for silo, it's microseconds.
But on the sort of few microseconds, hundreds of microseconds?
No, it's not hundreds of microseconds. It's few microseconds.
It's all main memory.
Some of these systems run multiple, a million plus transactions a second. Now that's using multiple cores, of course, but the latency of the transactions is not very big.
Yes, that's true. For that, yeah, maybe it can be acceptable, using ARM transactions.
Whereas here, actually on Shore, where the latencies are much higher, the 2x might be much more important than your 11x is on the
Exactly.
on the main memory.
And when you say microseconds, you're not talking about, are you talking about the 99th and 99.9 percentiles?
So
That's average.
That's quite a feat,
That's average.
right? If you can manage that at the very tail,
Yeah.
to be talking about a few microseconds, that just blows my mind.
No, but the few microseconds is the average, but I mean, the real point is, what is the latency actually out there? Does anybody care, right? I mean, but this is obviously something to watch, is this ability to handle interrupts and avoid getting tied up in a knot.
Yeah.
I mean, let's face it, there's 99.9% tail latency. I mean, that's always the case where things did not work well,
Yeah, absolutely.
by
Yeah.
definition, right?
Yeah.
Something went very sideways.
Yeah, well, for sure. Yeah, they're sort of outlier, but they can be improved. Trying to remember the
The
real
whole
numbers.
transaction is just.
I mean, yeah, for 99.99, if I'm not, it was around microseconds for sure, but maybe like around 100 microseconds might be. For average, it's for sure very few, like less than 1 microsecond. And towards the tail of the latency distribution, maybe it's around 100 microseconds, but it's definitely not in the orders of milliseconds. So it can be acceptable. I mean, it's a matter of choice for sure. Yeah, very optimized system. But it's in the design space. It shows that Xeon is significantly better than ARM. Okay, so this was the last graph. So okay, let's sum up. So server grade ARM indeed is a promising alternative. It's something that needs to be taken seriously. It provides substantial level of performance with low power consumption characteristics. It achieves energy proportionality at the processor level, no power waste during low load periods, and it's less suitable for latency critical workloads, as we've just discussed. So for the underutilization problem, now we have looked at the hardware aspect. We have compared Xeon and ARM 64 cores, and the question was, can we save power? It's yes, you can if you're not very sensitive on tail latency. You can have high throughput with low power, but if tail latency is a very big deal for you and your system is not able to tolerate this, then you might end up using only having only Xeon as your alternative. So this concludes the talk. Thanks for the attention. Any further questions? Go ahead.
You compared the energy efficiency of ARM with Xeon, going from 1 to 8 threads. In that case, on the Xeon, you were pitting 1 thread per core.
Correct.
What if you, instead of going 1 thread per core, you turned on hyperthreading and restricted yourself to just 4 cores, but you used more of the threads on it? You used all the threads on a core before going to the next.
I see.
How would that graph look?
So I hope I had it. Where are you? So we looked at hyperthreading, not in the exact same configuration that you mentioned. Come on, I don't have it. How can I not have it?
I don't know if you
have
have
a lot of them, but this is 86.8. So there, the energy efficiency of hyperthreading is 40% in the following configuration. You have 8 cores active, you have 16 cores active.
Will you share the slide deck with us?
Of course, yeah, sure,
Lovely.
pleasure. Yes.
You've got a lot of stuff in there, it's worth looking at.
Absolutely, a lot of results, and this is just a portion of it. So it's 8 cores active or 16 cores, make it hyperthreading. You have 20% higher energy efficiency, 40% more performance, and some more power consumption. So what you're saying is, can we do 4 cores and with hyperthreading and compare with 8 cores of ARM, right?
Right.
So in this case, okay, let's look at this. So in this case, what would happen is ARM's energy efficiency, like 4 cores, Xeon's energy efficiency for 4 cores, let's look at Silo, for 4 cores, would be 20% higher. If this is 20, if this is 100, then it would be like somewhere here. So it would be, less than, yes, it would be less energy efficient than ARM, but
See, what's
maybe
happening is Xeon is being designed, they've kept hyperthreading in mind.
sure.
And the microarchitecture is sort of tuned in that fashion. So when you hamper it by taking one thread out of play, then you're not really doing an apples to apples comparison at that point.
I see. But for example, here we turned off hyperthreading in the BIOS. Wouldn't that turn off this power component that actually would spend for?
Not necessarily, because you have so many power hungry structures. They not all of them can be switched off. For example, the reorder buffer, the size is decided based on the fact that you will turn on both the threads. The ARM may not have that larger reorder buffer. The reorder buffer is going to consume a decent amount of power. So it's something to keep in mind when you do these comparisons.
I see. That's a good point, actually. Sure. So it's not like it's having in mind. Yeah. I mean, yeah. It's in one sense what you're saying is true, right? I mean, maybe it's not apples to apples comparison because it's meant to be with hyperthreading. But even though when you have hyperthreading, its energy efficiency is not that high for Xeon. For transaction processing, typically it's known that hyperthreading is 2x, right? Like ideally, you have 2 logical cores. For transaction processing, typically you have 40% more performance when you have 2 cores, additional core, rather than 2x. So this is, cache pollution and so on for several reasons. So it's known to be not very efficient for transaction processing. But on the other hand, like this comparison might be a bit misleading in that sense. But this is sort of one point, using like heavily optimized aggressive processors for transaction processing systems, maybe is, not the best choice, maybe. But these are like all things that needs to be, analyzed, like different prefetchers. For example, this is enabled here, 4 prefetchers in the BIOS Xeon has. Xeon has 4 prefetchers. They are all enabled it, for example. Are they useful for OLTP? Are they not useful? How much power they consume? And all these structures, there are a lot of things that you can't turn off in BIOS. But overall, the perspective is, okay, this thing stalls a lot. Most of the time it's empty. And, let's use something simpler. Maybe you save some power, overall performance perspective. But for sure, like one-to-one comparison is indeed hard. Anything else?
So you have shown in one of the experiments where you increase the size of the transaction and you see the store of the CPU store actually decreasing proportionally, where you conclude that some of the CPU stores happen outside the OLTP engine.
Yes.
So did you do some sort of breakdown of the CPU stores that happen inside the core OLTP engine? Outside the
I see. No, I did not. I see what so you're saying, like in this graph. Let's look at this graph. That's a good point. Like here, how much of them are from inside the OLTP engine? How much of them? No, you're right. We haven't done this. I mean, this is like the closest thing that I can show you in that sense. As you increase this, number of rows read per transaction, the time that you spend inside is increasing. You can consider, for example, here, 40% of the time you are inside the OLTP engine, 60% of the time you are outside. For 10, here for VoltDB is 80% inside, 20% rest is outside.
Okay.
But like direct correlation to L1 instructions to that I don't have. But you can consider like more or less they are related.
Yeah, because for writing suggested what how we can optimize the OLTP engine to reduce the CPU stores. If most of them have outside the whole engine, or
I see. Then you do something
Yeah,
else.
yeah.
Yeah, for sure. That's true. Yeah, for sure.
All right, that's
Makes
thank you.
sense? Thank you. Thank you.